Algebra 2 trigonometry regions transformation video. Start off with a couple of properties. So these are transformation properties, and we have a bunch of them. But to best understand this, what we need is our calculator to help us understand what's happening here, and we need something that's called a parent function. So we're going to start off with a basic graph of y equals x squared. So let's say y equals x squared. We're going to call that our parent function. Basically, it's just kind of like what we're going to start with. And you should be familiar with y equals x squared. It's a parabola centered at the origin, and it looks exactly like this. So here's our parent function. Okay, just keep in mind what that looks like. All right, so our first property is saying that if you take your function and plus c, now c represents a constant here, and a constant is just a number. So if our parent function, again, we're using a parent function of just y equals x squared. A transformation of f of x plus c would be something like y equals x squared plus 3. And what this property is saying is that when you plus c on the end of a function, it transformed the function c units up. So what we're going to see is our parabola is going to be transformed or translated c 3 units up. So let's take a look at what happens when we do that. So if we turn x squared into x squared plus 3, notice that the graph has now been shifted up 3 units. And so that's what we end up with for that. I'm going to make it small and just put it right underneath it. So that's 3 units up. And then if we were to minus a constant at the end of the function, it'd be transformed c units down. So this kind of got cut off and shot to the next line there. It shouldn't be on your notes, though, on top of your page. This should all be together. So if I were to change this to be, say, y equals x squared minus 3, you're going to see the whole thing get transformed 3 units down. So let's change our plus sign to a minus. And so we'll see the regular graph that was centered here has now been shifted 3 units down. Now, slightly different is the comparison between f of x plus c and f of x plus c. Notice that this has the function ending with the parentheses, and then it's a plus c. This has in the parentheses plus c. And so that's a little bit different. And so the comparison on the calculator would be, instead of x squared plus 3, which we already did, it would be parentheses x plus 3 squared. Because what's happening, so in the parent function, you're squaring your input value. You're squaring x. And so for our original, it's that, and then just adding 3 on the end, and that's a shift up, or minus would be shift down. But if you do the plus or minus before you squared, that's a transformation side to side. So we know that the plus 3 shifts our graph up. Well, the plus 3 in parentheses shifts it to the left. And that's what this first, or this next property is saying here, that plus c in the parentheses is c units left. And I think the left is probably a little bit of a surprise. The plus is up and the minus is down when it's outside, and I think that is what you would guess if you had to, and it makes sense. But inside the parentheses, it might be a little counterintuitive. Plus actually means left, and minus is the one that means right. And so when we have a plus inside our parentheses like this, we see that moved the graph 3 units to the right. 3 units to the left, sorry. And if we are to change it to, again, a minus, that minus moves us to the right. And so from our origin now, the whole thing's been shifted over to the right 3 units. And so you really have to make a conscious effort to remember that, when it's inside the parentheses, plus is left, minus is right. And so that's your up, down, left, right. Outside is up, down, inside is left, right. Now there's a couple of things you could do. What if you were to multiply your function by something? And this has to do with stretching and compressing the graph. So if we were to take let me go back to my parent function here. If we were to take just our graph x squared, again, take a look at what that was, and I have those up here. How is that going to change if we were to make it, say, 3x squared? So we were to multiply 3 times x squared. And what's going to happen is it's a vertical stretch or compress. And so that's what's happening here is if you multiply a number in front of the function, like, again, what we're doing is y equals 3 times x squared. That's what the case is here. And since c is greater than 1, like in this case 3, it's a vertical stretch. And so what happened was our graph is being stretched vertically, and that basically makes it narrower. If the number that we multiply to the front is between 0 and 1, like say it was a half, it's going to compress it and actually make the graph wider. So if I were to change this to see 0.5 x squared, you'll see that the graph gets a little fatter, a little wider. The other case is a horizontal compress and stretch, and that's a little bit rarer. You don't see that as much. But that would be, again, like kind of inside the parentheses in a sense. Like if I were to do 3x in parentheses squared, what would happen there? And we could take a look at that too. But really the vertical, I think we see much more often. So there's your 3x, and then if we were to square it and then graph it, and you see it's almost like the horizontal compress and the vertical stretch are very similar. Both of those make your graph narrower. And so that's what's happening there. And then the last thing is reflections, that if we were to negate the function, so if we were to, say, reflect across the x-axis, if I were to change it from y equals x squared to y equals negative x squared, then that's going to reflect across the x-axis. So if we times negative in the front, so let's change our x squared to negative x squared, you're going to see it flipped across the x-axis and be upside down. And if you were to put the negative in the parentheses, now this maybe is a bad example, because if I do parentheses negative x parentheses squared, it's not going to look like it changed at all. But actually it did. It reflected over the y-axis, but because this particular graph is symmetrical across the y-axis, it actually didn't really change much. But you will see this one a lot, that when we put a negative, it flips it upside down and reflects across the x-axis. All right, so let's look at a couple of problems now that are going to use these properties. And you really just have to remember, plus or minus outside is your up and down, plus up minus down. Plus or minus inside is your left, right, plus left minus right. And then timesing the function is going to either stretch or compress it. And sometimes we refer to it in terms of narrower and wider. And if you were to negate the function in the front, it's going to reflect over the x-axis. So those are our big ones here. So compared to its parent's function, x squared, what effect will you see for f of x plus 2? So we have a plus 2 inside. That's going to be 2 units left. If it were plus 2 outside, then it would be 2 units up. Remember, plus inside means left. How about a minus 3 outside? Well, that's going to be 3 units down. All right, a couple things here. So our parent is square root of x. And then there's 3 things that are added to it. It's negated in the front, a plus 2 inside the radical, and a minus 3 outside the radical. So one at a time. First of all, negating the function reflects across the x-axis. So reflection over the x-axis. So now we're looking at these choices, not the y-axis. A plus 2 inside means left 2. And a minus 3 outside means down 3. So our answer there is that. Take a look at one more. Times 2 in the front, minus 4 inside, plus 6 outside. Times 2 is a vertical stretch. It's going to make it narrower. And minus 4 inside is to the right, plus 6 outside is up 6. And really, you could take a look at this on your graph and take a look at this on your graph and compare them to confirm these things. But knowing these properties offhand makes the whole thing a little bit easier. Okay, so that's function transformations. We'll practice it the next day.